Hello everyone and welcome to Sri Chaitanya IIT Academy, and we are continuing the paper discussion of JEE Mains 2021. So the first question here we have is a tricky one. We have a acid, that is your oxalic acid, and then we have glycol. So if you remove these water molecules, you're going to get a cyclic ester. And then you are again heating this entire thing at 210 degrees centigrade. Now this leads to pyrolysis of ester. So what happens is that whenever you heat a substance, always the tendency of volatile product formation increases, and CO2 is a volatile product. Now what happens? This electron comes here along with this. This bond breaks in this manner. I'm showing half-headed arrows because only one electron is moving. And as a result, we get two CO2 gases which flies off, and ethene is obtained as a product. So that means my answer is option number 2. This one is a tricky one. Next, we have the same question. It's been repeated from 24th February. Now we have aniline here, and these ingredients hints towards nitration. So just remember, for nitration, we have already discussed in our earlier papers that aniline in presence of acidic medium gets protonated and turns into anilinium ion. Now this anilinium ion is having this particular group which is strongly minus electron withdrawing, and as a result it's having that deactivating effect on the ring, and therefore we will obtain the meta product in a significant amount. So here this meta product is roughly around 47%. Ortho product is nearly very less, it's 2%, and whatever is left, that is 51%, we have the para product. So I give you a trick. You just remember PMO, right? Because this has been repeated, so chances are that it can be asked again. PMO means Prime Minister's office. That's the most powerful office in the country. So P stands for para, M stands for meta, and O stands for ortho. So para is the major one, and then we have meta and ortho. So which is the major product here? Para is the major product. So product number 3 is major product. No, it's not correct. Reaction is possible, and 2 is the major product. Yes, it is correct. Next, we have two statements. Normal rainwater has a pH of 5.6. Yes, we can take this to be correct because it varies from 5 to 5.5. Around something like that. Now acidic water, the pH will be less than that, right? Because if you are having oxides of sulfur dissolved in rainwater, the water turns acidic and pH is less than 5.5 or 5.6. So both the statements are correct, and we have 3 as an answer. Next, we have again something from biomolecules is coming up. We have a maltose here. Now they are asking the alpha anomer of maltose. Now maltose is basically a disaccharide of 2 units of glucose connected via a glycosidic linkage between C1 of one glucose unit to C4 of the other glucose unit. So as we can see, this is a glucose. This entire unit is glucose. If you put a OH here, this is the glucose, and this glucose is alpha glucose. Similar manner, if you put a OH here, then this will also become a alpha glucose, right? And now this one will be the 4th carbon, while this one will be the 1st carbon. So they are connected by C1 and C4. And since both of the units are alpha, so this linkage is alpha glycosidic linkage. They can connect them by removing a water molecule. That's how maltose is formed. So this is the appropriate option. Next, we have a order of Ka, or in short, they are asking the acidic strength. Now we know the electron withdrawing group improves the acidic strength. So if I go by that logic, we have nitro group here. So this is an electron withdrawing group, and therefore it is expected to be most acidic. And after that, we'll be having this electron donating group is going to decrease the acidic strength. So this is less acidic. So this is the first one in terms of Ka. We have found it out. Let's check our options. So we have only one option that says this. So definitely 3 is the answer. Now we have a series of conversions. We have starting with a benzene ring and we need to end up here. So what shall we do? Let's go and check the option 1. Now in option 1, we have Friedel-Crafts acylation, and after this reagent is subjected to, we are going to obtain what? We are going to obtain this particular product. Now we have this second one. This is nothing but Climation reduction. After we subject this particular reagent, the ketonic group will get reduced to an alkane. And then we have Br to an Fe, which means bromination will occur at the para position with respect to this ethyl group. Now, the last set of reagent, that is the fourth set, that is nitration reagent, and nitration will occur with respect to the activating group, and that is the ethyl. So ortho to ethyl will be putting the NO2 group, and that's how we're going to arrive at the desired product. So option 1 is appropriate. This question, we have again electrophilic aromatic substitution. So let us check. Now in presence of H plus, the pi electrons will get protonated. And as a result, there will be a formation of positive charge. So we know that carbocation is more stable when it is a higher degree one. But then if we put a carbocation here, it will be closer to NO2 group, which is not desirable because NO2 has a electron withdrawing effect. Now, because of the presence of NO2, the positive charge is going to get formed at this particular position. So this is the carbocation I have. Now this particular ring, that is the benzene ring, is going to attack at this particular carbon, and as a result we are going to get option number 4, right? Next we have oxo process. So this is a catalyst here, H2NCO. This is called oxo process. What you need to do, this is also called hydroformylation. You break the bond, you break the pi bond here, and one side you add CHO and the other side you add hydrogen. Now this can be done in one more way. One side you add H and the other side you add CHO. Now this product is the major product, and this one is the minor product. So as we can see here, the most appropriate option is number 2. Now in the estimation of halide from sodium fusion extract, that means we are talking about Lassaine's test, right? Which compound is used before adding AgNO3? So before adding AgNO3, what we use HNO3. Now, why we do that? Sometimes what happens, Cn minus remains or S2 minus, that is sulfide ion remains. So when we provide HNO3, these two type of ions, they get converted into gaseous substances and they fly off. So when these things fly off, the detection becomes easier for the halide ions. So we add here HNO3. Option number 3 is most appropriate. Next is information from metallurgy. German silver is an alloy of copper, zinc, and tin. So this is straightforward, nothing much to do. Next is in line, we have a question from halogens. They are asking about the bond energy. Now, halogens, they are having a pp overlap. There's a simple overlap between the p orbitals. Now, as the size of the p orbitals increases, the bond length increases, and therefore the bond dissociation energy decreases. But then there is a catch. Fluorine is expected to have the highest bond energy because the bond length is least among all. But due to a close proximity, there occurs a lot of inter-electronic repulsion, and as a result, the bond length increases. And therefore, the bond energy in case of F2 is significantly low. Now, if we compare among the others, Cl2 should be, Cl-Cl bond energy should be the greatest. Then we have Br, and then we should have iodine and iodine. But then because of this repulsion, the bond energy of FF is also decreased, and it falls below Br, but above II. It falls somewhere here. If you go in calories, it's something around 58 kilocalories. It is 46 kilocalories. Uh, fluorine is roughly around 38 kilocalories, and iodine is roughly around 36 kilocalories. So if I go by that, I have option 1 most appropriate. Next, we have which of the following is false. The keyword here is false for hydrophilic salts. Now, hydrophilic salts, you just go by common sense. What is there? There's an affection between the dispersion phase and the dispersion medium. So when there's an affection, or when there's a strong bonding, that will make the things slow. So viscosity of hydrophilic salts are greater than the dispersion medium. So they are asking for the false statement. So option number 1 is false. Next, we have more than one type of bond length present. So that means we should think about something like sp3d or sp3d3. Straight away, we have uh, among this, we have option number 4. If you clearly see the steric number, we will get a hybridization of sp3d, which is trigonal bipyramidal geometry with a lone pair. Now, we know the lone pairs are having a preference to occupy the equatorial position, and will be placing the lone pair in an equatorial position, and remaining fluorines will be adjusted rest of the places. So here we are getting different type of bond lengths. These bond lengths are equatorial, whereas these two bond lengths are axial. Next, we have alpha sulfur and beta sulfur. Alpha sulfur is nothing but rhombic sulfur, that is S8. Beta sulfur is nothing but monoclinic sulfur, that is S6. They are reversibly converted to each other under slow heating. Oh, actually, the thing is that S6 exists only above a temperature of 95.6 degrees centigrade. That means below 95.6 degrees centigrade, alpha sulfur, that is the rhombic sulfur, is the most stable form. So statement 2 is clearly incorrect. Monoclinic sulfur exists at room temperature. No, it exists above this particular temperature. So this is a wrong statement. Huh. Alpha sulfur and beta sulfur, they can be converted to each other. They can be converted to each other under slow heating. No, they cannot be converted to each other under slow heating, only at that particular temperature. This temperature is also called transient temperature. So this statement is also false, and we arrive at option number 2. Both the statements are incorrect. Next, we have Ni plus 2 is detected by DMG and ammonia. Yes, true. Ni plus 2, this is the confirmatory test. We will use DMG in a medium of ammonia to arrive at this particular complex. And this is green in color. So this is the confirmatory test. Everybody knows this is true. Now, DMG is a neutral bidentate ligand. Yes, this is your DMG. So this is your DMG. When one of these hydrogens are removed, there appears a negative charge. Then it becomes dimethyl glyoxymato. But you are talking about dimethyl glyoxime. So this is dimethyl glyoxime, and it is a neutral bidentate ligand. So this statement is true. So we arrived at option number 1. So both the statements are true. Next, we have a question that is very simple, KSP. So for this particular sparingly soluble salt, if I consider the solubility to be S, solubility product KSP will be nothing but 4S cube. So this 4S cube is equal to 5.5 into 10 to the power minus 6. So from here we can calculate S. Now if I go and calculate S, I'll be getting 1.1 approximately into 10 to the power minus 2 molar. So 1.1 into 10 to the power minus 2 molar, that is option number 1. Next we have a set of complexes, and we have to arrange them in the order of spin only magnetic moment. Okay, let's start. Here we are having Fe plus 3, and this is present in the ligand field of F minus. And if this is present in the ligand field of F minus, which is a weak field ligand, there will be no back pairing, and the configuration will look like 3d5 high spin. So that means we have 5 unpaired electrons here. At the same time, we talk about this particular compound or complex Ni plus 2. Again, it is present in the field of Cl minus, which is again a weak field ligand. I'm going by VVT. So Ni plus 2 will have a configuration of 3d6. I think 3d8. Let me correct this. Now here, if it is a weak field ligand, how many unpaired electrons will be there? 2 unpaired electrons will be there. Now, if I talk about this third one, cobalt plus 3, right, in the field of ammonia. So in the field of ammonia, ammonia is a strong field ligand. CO plus 3 is having a configuration of 3d6. And if it is a strong field ligand, back pairing will occur. And if back pairing will occur, then number of unpaired electrons will be 0. Now we have this particular second one. The second one is a little bit trickier complex. Here we have a phenomena that is transference, right? Associated with this particular complex, we can see that Cu plus 2 and in the field of ammonia. Now ammonia is a strong field ligand, back pairing will occur, but then there is no room for back pairing. So only one, this is going to give you the configuration 3d9, which is going to have a state, a number of unpaired electrons that is equal to 1. So if you carefully observe the number of unpaired electron in all the cases, we get at our answer. So highest is Fe F6, then we have NiCl4, then we have copper and ammonia, and we have lastly cobalt and ammonia. So this is the correct option. Next we have, which of the following cannot form CO on reaction with H2O? Now this is coming from preparation of hydrogen in the chapter hydrogen. So hydrocarbons, whenever they are subjected to steam, we get hydrogen and CO. Carbon also, when subjected to steam, we get CO and H2. Remains this one. So this makes my answer. Indium is refined by zone refining. Very factual, because ultra pure metals are generally refined by zone refining method, because in this method high purity metals are obtained which are needed for sophisticated applications. Next we have a question from electrochemistry, and they are asking uh, to compare, right? So let us start with the question. So we have to consider here two redox reactions, copper plus 2 NO3 minus plus 4H plus. I'm writing the balanced form of the reaction. So this is uh, the reaction when NO3 minus is getting converted into NO2. Now, if I write down the Nernst equation, NO3 minus getting converted into NO2 in acidic medium, what will be that? That will be simply E naught value, which I'm writing here to be E1 minus 0.059 divided by 2 log of 1 upon x square multiplied by x to the power 4 into concentration of copper plus divided by already we have written the concentration of HNO3. Say for example, they are asking, I'm assuming it to be x. Therefore, we have a x square here and x to the power 4 here, and pressure of NO2 to the power 2. Now they are asking to take the pressure of all gases to be unity. So this goes out. Second, we have the concentration of copper plus 2. So copper plus 2 concentration is also not given in the question. And as I do not have it, I will assume it to be 1. Otherwise, I cannot solve the problem. So if I simplify this one, in the given data, this value is 0.79 minus 0.79 minus 0.059 divided by not 2. If I see the number of electrons involved, it's 2 only. Log of 1 upon x square into 1 upon x to the power 4. So if I simplify this one, 0.79 plus 0.59 into 3 log x. So this is what I'm getting. Now, when NO3 minus gets converted into NO, the reaction will look like this: copper plus NO3 minus plus H plus. The reaction is going in acidic medium, Cu plus 2, NO plus H2O. Now I'm writing it the balanced form directly. This is the balanced form. A 2 will suffice here and a 4 will appear here. And if I apply the Nernst equation, NO3 minus changing into NO in acidic medium, this will be equal to E2 naught minus 0.0591 divided by the number of electrons. Here, the number of electrons taking part is 6, multiplied by log of, you see here the pressure of NO2 will disappear, pressure of NO to the power square will disappear, multiplied by concentration of copper plus 2 raised to power 3 divided by x square multiplied by x to the power 8. Now, since like the earlier time, we will assume it to be 1 and also assume it to be 1. And this further simplifies into 0.96 plus 0.0591 divided by 6 into 10 into log x. Now, at what concentration they are asking, the tendency will be same. That means this electrode potential value, this value and this value will be same. So you have to equate these two parts. And when you equate these two parts, you will get the solution of the value x. Now, when you do so, your x will come out to be 144 approximately. Next, we have inline is a question, spin only magnetic moment for the divalent cation of this. So Z equal to 29 is nothing but copper, and divalent means copper plus 2. So copper plus 2 contains only one unpaired electron, that is N is equal to 1. So spin only magnetic moment is given by this particular formula, N into N plus 2 Bohr magneton. So you put the value here, you'll get the answer, and that will be root 3 Bohr magneton. Next we have is a question. from kinetics. And we see here that when the temperature is raised from this particular value to this particular value, the rate of the reaction becomes 5 times. We have to determine the activation energy. So we will use the Van 't Hoff equation, log base 10 K2 divided by K1, and this is equal to activation energy divided by 2.303 R 1 upon T1 minus 1 upon T2. Now, what is T1? T1 is the lower temperature, that is 300 Kelvin. And what is T2? T2 is the 52 degrees centigrade, that is 325 Kelvin. Now, if you work on this and simplify, you are going to get log 10, base is 10, value is 5. Activation energy, which I need to calculate, 2.303 into 8.314, and multiplied by, when you simplify this, this will become 300 into 325. Now you work on this and you get activation energy approximately equal to 51.74 kilojoule per mole. Next we have a question from solution. That is the colligative properties, again a very hot and popular topic. So what is the thing? This AB is dissociated into A plus and suppose B minus. And initially, if you are having N naught moles at T equal to 0 till the establishment of equilibrium, some will dissociate, that is N naught alpha. So we'll subtract that, and here N naught alpha, we will add it. So how to calculate Van 't Hoff? What is the total number of moles at equilibrium? You add them. So you're going to get N naught plus N naught alpha divided by N naught, which is equal to 1 plus alpha. Now alpha is given as 75%. So alpha is equal to 0.75. So we can get the value of I. Now we will find delta TB, which is equal to KB times of I times of M. Now KB is your 0.52, I is 1.75, and molality is not given. So we have to find molality. But the delta T is given, that is 2.5. So you put these values here, and if you put these values here, you're going to get molality something approximately equal to 2.7. Next, we have another question that is asking about the structures. So structures are becoming important these days, and some structures are very important. So say, for example, sulfenilic. It is this particular structure. So this is sulfenilic acid. Picric acid is again very popular. One is expected to know picric acid. You put 3NO2 group in a phenol, it becomes picric acid. Then you have aspirin, again, very, very popular one. So everybody should know about aspirin. And we have ascorbic acid. So this is something different. Ascorbic acid is nothing but vitamin C. So if you don't know this, that can be understood, but others is expected to be known by a serious aspirant. So this is your ascorbic acid. So what's the question? How many groups contains carboxylic functional group? So only one, I guess. This is the guy, right? So next we have in line is the question where they are asking density. So this is copper having a FCC lattice. So what we do, mass divided by volume is nothing but density. So Z, the number of effective number of atoms per unit cell in an FCC, that is equal to 4. So that is Z multiplied by the atomic mass. Atomic mass of copper is 63.54. So let me write down the mass itself. Atomic mass divided by A cube, that is the volume of the unit cell, multiplied by Na. Now when you simplify this, 4 will come here, 63.54 will appear. Now what is the length of the unit cell? That is 3.69 angstrom 10 to the power minus 10, and you cube it multiplied by Na 6.02 into 10 to the power 23. Now, when you simplify all this, approximately it comes around 8.4 gram per ml. Next, we have what is the value of energy in kilojoule for light, okay, which is having a wavelength this much. So this is also very easy. Energy can be written as hc by lambda, but they are asking in kilojoule per mole. So you need to multiply this whole thing by Na. And since they're asking in kilojoule, you have to again divide it by 1000. So you put the values here, that is 6.626 into 10 to the power minus 34 joule second multiplied by 3 into 10 to the power 8 meter per second divided by lambda, that is 633 nanometer, which is 10 to the power minus 9 into 1000 here and here 6.02 into 10 to the power 23. You simplify all this, you are going to get energy something very close to 181 kilojoule per mole. Next, we have how many of the following metals are used in the photoelectric cell. See, this question has been asked last year also, but in a different format. So you should know cesium and francium, they are used in the photoelectric cell because of the attribute that they have, which is their IE is very less. Down the group, ionization energy decreases. So cesium. Next we have is a question of titration. So they are asking the molarity of NaOH. So the titration has been iterated 5 times and these are the readings. So we'll go by the most common reading, that is the most probable reading. That is, I will consider this data. So what I can write is the milli equivalence of NaOH and milli equivalence of oxalic acid. There has to be same milli equivalence of NaOH. What will I write? Volume. I'm taking 4.4 because that is more common, multiplied by the molarity. How much is the molarity? We don't know. We have to find it out. Milli equivalence of oxalic acid. 10 ml is the volume. Molarity is 1.25, but then this is dibasic, so you need to multiply by 2. And when you solve this one, I think you are going to arrive at something like 5.68 molar. So you're going to take the nearest integer or decimal as per the instruction. Question number 29 is the next question. 5 moles of an ideal gas is expanded at constant temperature from 273 Kelvin from initial pressure of this one to this much. So they are asking the heat, how much is the heat exchanged? And this happened at a constant external pressure of this much. So what we do, let's find out the V final. So V final is nothing but nRT by P1, nRT by P1. So this is like my P1 value. And this is like my P2 value. Temperature is already given to you. This is the temperature value. 5 moles, this is the N value. So R we already know. So I'm going to put R in SI units. 5 into 8.314 multiplied by 273 divided by 1.3 into 10 to the power 6 meter cube. You simplify this, this will be roughly around 0.087 meter cube. Now similarly, we can find V initial, V final. Okay, let me do one thing. V final is the final volume. So in final volume, this is P2. This is P2. So here we will be using P1. So that is 5 into 8.314 multiplied by 273 divided by so what is the initial? We have to take 2.1 here. Right, so when you do this, you are going to arrive at 0.054 meter cube. Now, what is work done? We all know P external dV. Now, when the pressure is constant, you can take that out and it simply becomes delta V. P external is equal to V final minus V initial. So you put the value there, you can arrive at some answer, and that will be roughly equal to minus 1.36 joule. And since everything has happened at constant temperature, delta U will be 0. If delta U is 0, Q is equal to minus W. So minus W now will become 1.36. There may be an error in the calculation. You can check it. But this is how you have to proceed. So this is the end of it. There's one question short. Our students might have missed that out because it's not very easy to remember all the things in a stress-like situation, right? I hope you're doing well. Thank you very much.